Okay, so let's jump right into chair conformations. We've talked about Newton projections on cyclic compounds. Now we're going to apply that to six-membered rings and look at what happens when we use things that are more complicated than just cyclohexane, right? All right, so in the previous video, we looked at six-membered rings and we said if we draw a Newton projection of that, right, we end up with something that looks like this, right? Where these are ghost to each other. So if we want to draw this back as a regular structure, right, what we'd have is we'd have hydrogens, 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 and then we'd have this bond going back, and then we'd want these to be kind of anti, or not anti, but staggered with that. So whereas this hydrogen is going down, this hydrogen is going up, or this hydrogen is going to the left, this group is going that way, and then we go like this. And then we would just do the same thing on the other side. We would end up with a structure that looks like this. This is called a chair conformation. I'm going to draw it without the hydrogens in there. So now this is a chair conformation, and you're probably thinking, that doesn't look anything like a chair. And I pretty much agree with you. It doesn't really look anything like a chair. Supposedly this is like the footrest and this is like the headrest, which kind of makes me feel like it's a dentist chair or something. Like here's your headrest up here, right? And then your foot. So it's supposed to be like a recliner. I don't know. It's a stretch, but hey, everybody calls it chair conformation, so we're going to call it chair conformation, and we'll go from there. But what this chair conformation does is, right, you have all these gauche interactions. So we saw over here that these two carbon-carbon bonds are gauche to each other. Sorry, I'm using the wrong pointer. Over here, that these two carbon-carbon bonds here and here are gauche to each other. And so when we draw the chair conformation, those are gauche to each other. These are gauche to each other. These are gauche to each other, and so on and so forth, right? What this does is it sets up every position on this molecule now there's only certain places that the other groups can go, right? So in each position, we have two other groups, right, that have to go into these other two positions that would be on the Newton projection, right? And so a chair conformation looks like this. Now, if we were to, let's take this Newton projection, let's say instead of doing just cyclohexane, I was going to make methyl cyclohexane. Right, so I'm going to put a CH3 group on there. If you were to replace one of these hydrogens with a CH3, which position would result in the most stable replacement? Okay. So if we're thinking about it, what we would want to do is we'd want to make most stable, we'd want to place the CH3 group anti to the largest group on the other carbon, right? And that's just our Newton projection 101 on the other carbon. Right? And that's what we do with Newton projections. And so we look at these and of these options, right? If these are the largest groups over here, the best options are going to be one of these two hydrogens. And it just depends on which carbon you want to put your methyl group on. So there's really two options. You could do this one with the methyl group there. Oops, that's not a hydrogen. Pardon my mistake. Right, so there's your six-membered ring, but notice that the methyl group is anti to this group. Right? It's 180 degrees from that group. And so this is the most stable position. Now, let's translate that up to our chair conformation, right? Those positions that are anti to the rest of the ring, those are the positions, I'm going to circle these in red. Those are the positions that look like this, it looks like this, it looks like this, here, here, and here, right? All of these positions, if you look at where those bonds are, right, they're 180 degrees from the parts of the cyclohexane ring, right? And you can do the same thing over here. If we look at this one, look at this bond, it's 180 degrees from this bond right here. It's 180 degrees from this bond right here. Right? And those are the ones that are going, so if we put a methyl group on here, we want to put it in one of these 6 positions, depending on which carbon we're looking at. So these positions that I've just circled, the circled positions are these anti-positions are called equatorial, right? And the reason is they're kind of pointed, if you imagine the chair conformation as like a globe, I guess, right? The equatorial positions all kind of point out along the equator, right? They all point around the middle of the ring, out away from the ring, as opposed to the other groups, which I'm going to redraw. So the anti-positions are in red, or yeah, the anti-positions are in red. That's the equatorial positions. If we now draw, let's see if I can, I'm going to draw one more chair. Right? If we now draw just the other positions, right, you'll notice that in each one of these positions, there's either a hydrogen going straight up or there's a hydrogen going straight down off of each carbon. I'm going to draw those in green. See how that goes. Right, so at each position, we're going to have kind of a hydrogen that goes along the vertical axis of the globe, if we imagine the cyclohexane as a globe still, right? And so these gauche positions are axial, right? So this is the axis, right? And this is the equator that kind of goes around the middle. Axial, equatorial from there. Okay? Now, the important takeaway point is that if we have large groups, they will always be more stable in equatorial positions, right? And the reason for that is the same reason, where did we go, right? Equatorial. The reason that they're more stable in the equatorial positions is that it minimizes that steric repulsion and allows it to be anti to the large group that's on the other side. Okay. All right, how to draw a chair. How to draw a chair that doesn't look anything like an actual chair. All right, so there's a couple of ways to do it. I think the easiest way is to draw 2 slanted parallel lines and then connect them, go up, whoop, see how easy this is? Goodness gracious. All right, so go up, when you start from the bottom, go up first and then down. And when you start from the top, go down first and then up. And that's your chair. And you'll probably have to fudge it a little bit, just like I did there, to make it work. I usually draw mine like this. So I start with these 3 and then come back to it. I don't know. There's a lot of different ways. But once you've drawn your chair, so here's our chair, right? Once you've drawn your chair, you're going to have, so there's going to be basically 2 types of carbon on here. There's going to be carbons that are peaks and there are going to be carbons that are valleys, right? So I'm going to circle the peaks in red, right? These are the ones that go kind of, well, they're kind of pointed up, right? And then I'm going to circle the valleys in, I guess I'm doing green since I've been doing red and green, right? And the valleys are down here, right? So you have peaks and valleys, valleys and peaks, valleys and peaks. So at the peak positions, the axial hydrogens or the axial group will always point straight up. Axial group points up, right? At the valley positions, of course, it goes the other way. All right. I guess I've committed to this changing colors thing, so now I'm going to have to do that. So for valleys, axial groups point down, right? And remember that when we talk about axial groups, we're talking about things that point straight up or straight down. So if we draw our axial groups in here at this position, right, at all the peak positions, we're going to have these go straight up. At all the valley positions, it's going to go straight down. Right? So that one kind of goes behind. Then the equatorial positions are going to be basically you're going to kind of balance it out. And so the equatorial positions, if the axial is going up, the equatorial goes out and down a little bit. So the equatorial or the axial goes up here, the equatorial goes out and down a little bit. Axial goes up, the equatorial comes out and down. Now remember that this line should be parallel to the or anti 180 degrees from the bonds of the ring, so it goes there. When the axial group is down, that means that the equatorial group goes up and out, up and out, and up and out. So you can get stuff that looks like that. Now, if you really want to get fancy, you can start stitching these guys together. Okay, so I put my equatorial groups on there, and that's just the start of another chair. Wow. Okay, except that you have to actually draw it well. So that's the start of another chair. And you can keep going, right? And then you can, if you really want to get fancy, you can start adding them together. This is actually the structure of a diamond. Diamonds are just a whole bunch of tetrahedral carbons all stitched together like this. So, which is fun, but whatever. Okay, but these are the axial and equatorial positions. At the peaks, the axial is up. At the valleys, the axial is down. And the equatorial is always in the opposite direction, but also pointed out as opposed to it's not straight up and straight down, right? The axial is straight up, the equatorial is kind of out and down. Okay. All right, so one more video on cyclohexane rings. We're gonna do some, we're gonna flip some chairs. So if organic chemistry has ever made you want to flip a chair, here's your chance, right? We're gonna flip some chairs. So we're gonna convert between axial and equatorial positions on the same molecule, and we're gonna do that by rotating the bonds that we, so just like we did with the Newman projection. So we're gonna be able to move things out of gauche conformations and into anti by rotating things, and we're going to look at what that looks like. So that's the next video. Stick around for it. You won't want to miss it.